In an incredible first, astronomers have discovered what lies at the core of Mars. It turns out the red planet isn't as lifeless as we once thought. Mars wasn't always a dusty, barren world. There's plenty of evidence that the planet was warm, had lakes of liquid water, and was habitable for a short period in its history. Astronomers had always wanted to know the reason behind this transition, and for that, they had to know what lies at the core of Mars. When the InSight lander started studying the planet's interior, it discovered that the planet is still rumbling with seismic activity. Now, following a rigorous half-decade mission, InSight has granted scientists a clear vision of the Martian core. So, how does Mars' core differ from Earth's? What methods did InSight employ to unveil the core of the red planet? Finally, and most importantly, what does it tell us about the future of our planet? Before understanding what InSight did at Mars, it's important to know how the mystery of Earth's core was cracked more than a century ago. It's all a play of waves. To decipher Earth's internal structure, scientists typically analyze seismic waves, shock waves that traverse the Earth's interior. These waves might originate from natural phenomena such as earthquakes or from man-made sources such as controlled explosions. By examining how these waves behave as they pass through different materials, seismologists can infer the properties of the materials traversed. Just as light waves interact with an object by being transmitted, reflected, absorbed, refracted, polarized, diffracted, or scattered, depending on the object's composition and the light's wavelength, seismic waves also alter their behavior based on the materials they encounter. Seismic waves come primarily in two types: P waves and S waves. P waves, or primary waves, are compressional waves that cause rocks to vibrate parallel to the direction of wave propagation. Being the fastest seismic waves, they're the first to arrive from the earthquake's epicenter. S waves, or secondary waves, are shear waves that cause rocks to vibrate perpendicular to the direction of wave propagation. They travel roughly 60% of the speed of P waves, arriving after the P wave is passed. In 1906, seismologists discovered that seismic waves move significantly slower through the Earth's core than other sections. More intriguingly, they observed that S waves failed to penetrate the core, while P waves traveled through it but were deflected at the core's boundary. From these observations, they deduced that the outer core is liquid, while the mantle above it is solid. Subsequent studies further enriched our understanding of Earth's core. In 1936, researchers noticed that seismic waves bounced off the inner core, suggesting a transition from a liquid to a solid state. These groundbreaking discoveries, all derived from meticulous seismic studies, have helped demystify the complex layers of our planet's core. Now, let's fast forward nearly a century to explore the Martian interior, where researchers have applied similar seismic techniques with astonishing results. Launched in 2018, the Mars lander InSight, an acronym for Interior Exploration Using Seismic Investigations, Geodesy, and Heat Transport, was designed for comprehensive analysis of Mars's crust, mantle, and core. A key part of this mission was to deploy a seismometer, known as the Seismic Experiment for Interior Structure, on Mars' surface. This instrument was designed to measure seismic activity and generate precise 3D models of the planet's interior. During its 4-year active period, InSight detected hundreds of Marsquakes. However, it was in 2021 when things started to get truly interesting. In this year, InSight documented 2 significant events on the opposite side of the planet. One of these was a massive Marsquake, larger and more powerful than any previously detected, while the other was a meteorite impact that shook the planet. These events, occurring on the far side of Mars from InSight, presented a unique opportunity. The lander was now able to analyze waves that not only traveled around Mars, but also through it, giving researchers an unprecedented look at seismic waves traversing the Martian core. The intrigue continued as scientists compared the travel times of these seismic waves through the core with those remaining within the Martian mantle. By integrating these data with other seismic and geophysical measurements, they were able to estimate the density and compressibility of the materials the waves traversed. The findings were unexpected. Mars's core seemed to be a squishy liquid throughout, contrasting with Earth's core that likely consists of a liquid outer core and a solid inner core, possibly containing an even denser innermost core. Furthermore, it was found that Mars's core had a high proportion of lighter elements interspersed throughout. On average, these elements contribute nearly a fifth of the planet's weight, with sulfur being the most prevalent, followed by smaller amounts of oxygen, carbon, and hydrogen. This unexpected composition further emphasizes the uniqueness of Mars's geological makeup. These findings indicate that Mars's core is less dense and more compressible than Earth's. On Earth, the magnetic field is sustained by geodynamo activity within the core. In layman's terms, heat travels from the inner core to the outer core, instigating currents in the conductive fluid within the mantle. As the planet rotates, these currents can twist into patterns, generating a magnetic field. This magnetic field then interacts with the fluid motion to produce a secondary magnetic field, a phenomenon known as the dynamo effect. This mechanism underlies Earth's self-sustaining magnetic field. Previous studies on Martian magnetism suggested that the presence of lighter elements in the core may have significantly contributed to the loss of its dynamo, and consequently, its magnetic field. Now, with a more comprehensive understanding of the Martian core's composition, we're better equipped to reconstruct Mars's history with enhanced accuracy. The characteristics of a planet's core provide an encapsulation of the planet's formation and evolutionary history. For instance, the unique composition of Earth's core enables it to generate a magnetic field that shields us from solar winds, preserving our planet's water and facilitating the proliferation of life. Conversely, Mars's core does not produce this protective shield, rendering it inhospitable to known life forms. These investigations not only help us identify potentially life-supporting alien worlds, but also enhance our understanding of the diverse ways planets can form, grow, and evolve over time, even when they originate from similar materials around the same star. Though the InSight mission concluded in December 2022, the high-quality data it gathered during its 4-year exploration of Mars will continue to impact our understanding of planetary formation and evolution for many years to come. It is a testament to the enduring value of scientific exploration and discovery. Recently, astronomers discovered that the dent in the Earth's magnetic field is getting worse. It's cracking open over a specific place on our planet. If you missed this episode, be sure to catch up on this intriguing discovery.